Hello and welcome to this video lesson. In this video lesson, we will be talking about optimization using graphical techniques. Imagine that you're given a sheet of size 20 by 10 centimeter. What you're going to do now is you are going to take scissors and actually cut this section over here, which is kind of like a square section. And for this first shape, you cut off 1 centimeter by 1 centimeter from 4 different corners of the box. And what you do after you get this shape, you start folding in this part over here. So we're gonna fold this in, fold this section in, fold this parts and these edges in, and then we're gonna tape it, and we're gonna get this shape over here. So we're gonna get a box, and the box is going to be open. So this surface over here is going to be here, and the bottom part is actually going to be open. Our task now is to see which size of a cutout length will actually give us the maximum volume, and we call this maximization of volume or optimization of the volume. So we want to choose a cutout length that will give us the maximum possible volume that we can get from this sheet of paper or cardboard. Now, we have 3 different boxes here with different lengths, so let's kind of talk about that first, and then we're going to talk about a general case. So, in the very first part over here, this side over here is 20 centimeters, and you're cutting off 1 centimeters from each side, and that's becoming the length of your total box. So, I'm going to make some labels here. So, this length over here is 20 minus 2, because you're cutting off 2 1 centimeter cutouts, so it's going to be 18, and this side over here is 10 minus 2, or simply 8. So on our box over here, this one is going to be 18, this one is going to be 8, and this one is going to be 18, this one is going to be 8, and this cutout length, you can see that this height of the box is the same region that we folded here, and this region is the same as the cutout length. So this one over here is actually just 1 centimeter for the very first one. So to find the volume of our box, we have to multiply length times width times height, and in this case we have 18 times 8 times 1. And these numbers simply multiply to 144 centimeters cube is the volume that I get if I were to fold a 20 by 10 centimeter sheet of paper with a cutout length of 1 centimeter. Now let's see what happens if I cut out 2 centimeters instead of the 1. So now what we see is our length over here is 20 minus 2 minus another 2. So that will be 16. And this length over here is going to be 10, which is this whole side over here. 10 minus 2 minus another 2, which would give us total of 6. And our height, just like before, in this case over here, is just our cutout length. So it's just this length over here, which is just 2. So in this case, our length is equal to 16, our width is equal to 6, and our cutout length or our height is equal to 2 centimeters. And for our volume is equal to length times width times height, which is equal to 16 times 6 times 2. And once I multiply these together, I will actually get 192 centimeters cube, which is actually a larger volume than this one. So that means, oh, as we're increasing the cutout length, then we're actually increasing our volume. So for the next case, let's try 4 centimeters and see if that's going to give us a higher volume than this, or if the pattern continues to go on like this. So for the next one, the horizontal section is 20 minus 4 minus another 4, because there are 2 cutout lengths, and that would give me 12 centimeters. And this length over here, which is kind of my width, is it's 10 minus 4, which is 2 centimeters, and my cutout length is 4 centimeters. So my length is 12, my width is 2, and my height is 4 centimeters. And if I want the volume, I do length times width times height, which is equal to 12 times 2 times 4. And that gives me 96 centimeters cubed, which is actually smaller than what I used to get, meaning that something is actually happening, which is actually pretty awesome. You can see that volume was 144, and then it increased by not so much, because we increased the height by a factor of 2, but the volume just increased by a little bit, and then we increased it by a factor of another 2, the cutout length, and it decreased our volume by approximately a half. So, and it kind of makes sense. If you look at this box, if we make this box, what we get is, if I draw it out, we get a very small surface area on top, and we get a we get kind of a tall height, and it actually doesn't give us as much volume as the first one. I kind of over exaggerated this in terms of drawing. Should have kind of ended right there. And the volume is actually smaller than the volume in the very first case, not by too much, but by a slight amount. So now the question becomes, what is the optimum cutout length which would give us the highest volume? And to do this, we actually have to solve it algebraically. And what we're trying to do is figure out the optimized cutout length. So we're going to label this as x instead of giving it a value, and then try to solve that x value, which gives us the highest volume. So you kind of have to come up with an algebraic expression for our volume, but this is not that challenging actually, because we know that this whole length over here is 20 centimeters, meaning this length over here, which is the length of the box, will end up being 20 minus 2 cutout length, and each cutout length is going to have a value of x, so it's going to be 20 minus x. And we know that this whole section over here is 10 centimeters, meaning that this portion over here, which is the width of our box, is going to be 10 minus 2x. And if I write everything down, I can see that my length is going to be 20 minus 2x. My width is going to be 10 minus 2x. And my height is simply, again, just similar to every other case we've done, is just the cutout length, because that's what I'm folding to make the box, and that's simply just x. And you can actually test to see if this works. So if I have a cutout length of 1, that means I can plug in 1 into this equation, and it becomes 20 minus 2 times 1, which is equal to 18, which is what I had here. 10 minus 2 times 1 is 10 minus 2, which is 8, which is what I had in the first case with cutout length of 1. And my height is simply x, or just 1, which is exactly what I had. And you can plug in all these values and you should get the same thing. So my volume in this case is equal to length times width times height. and my length is 20 minus 2x, my width is 10 minus 2x, and my height is x. And this is my volume over here. So my volume is 20 minus 2x multiplied by 10 minus 2x multiplied by x. And you can see that on the left-hand side of the equation here, I have volume, which is what I'm trying to kind of find what is the maximum volume. And it's written in terms of only one variable. So when you can see on the right-hand side, we only have one variable. In this case, we can say that the volume is written in terms of x. So V is written in terms of x. There's no other variables on the right-hand side, and therefore the volume is written in terms of x. In this case, x is our cutout length. And what we're going to do next is figure out how can we use this idea to find the maximum volume and what cutout length actually gives us that maximum volume. Alright, so we looked at this box, and this box, we figured out that the width of the box was equal to 10 minus 2x, the length was equal to 20 minus 2x, and the height was equal to x, giving us a volume of 10 minus 2x multiplied by 20 minus 2x multiplied by x. The other thing that we would actually, it's a good thing to actually take note of is how much is the maximum value that you can actually cut out. So we can see that on this side I have, and the smallest side that I can cut out from is actually this one, which is the 10. And if I cut out from this side, if I cut out 1 from both sides, I will have 8 left. If I cut out 2, I will have 6 left. If I cut out 3 from each side, then I only have 4 centimeters left here. If I cut out 4, I will only have 2 centimeters left over here. And if I cut out 5, I will actually have a 0 length over here. So one thing you want to kind of take note of is what is the limitation of some of your variables. And in this case, the maximum value that the x can be is actually 5, because anything more than 5 will mean that I'm cutting out, I can't actually make a box. So to get that value mathematically, we have to kind of use a little bit of logic and say that this side over here, which is our width, is actually 10 centimeters. And we know that 10 minus 2x has to be larger than 0, because this width over here always has to be larger than 0. We know that. So to solve this, and this is an inequality, we are going to add or subtract 10 from both sides, and we get negative 2x is larger than negative 10. We then have to divide both sides by negative 2. And by doing that, because this is an inequality, we actually have to change our sign. And negative 2 divided by negative 2 is 1, and negative 10 divided by negative 2 is positive 5. So we get that x has to be smaller than 5. So that's one of the limitations, that our cutout length has to be less than 5. We also know that our cutout length, if it's less, it can't be 0. That means we can't have a cutout length. And it pretty much has to be bigger than 0, otherwise we can't make a box. So we also know that x is larger than 0, which gives us this limitation where x has to be between 5 and 0. anything larger than that, then in our real life situation over here, we actually can't get a box. Now, we have come up with this equation over here, which is our volume, and we have our limitation of the x value, but in which x value gives us the highest volume, and that's what we're trying to solve. And there are many different methods of solving this. We are just going to look at the graphical method. And I will put up a link to how to use the TI Inspire 80 or TI 84. So TI 84 or 84 plus and TI Inspire. These I will put the link in the description to kind of give you an idea about how to use your calculator, if that's your calculator. If you have another graphing calculator, just use that. I am sure you can find a YouTube video or a video that can help you with that. Just for terms of illustration, I am going to use another website which is very useful but to use. So if you don't have a calculator, then you can follow this video using this package. So my favorite website that allows you to do some of these graphing work, and this is probably at the moment my favorite graphing calculator, is on a website called Desmos. So I'm just gonna click on it, and the website is called desmos.com/calculator, and I am going to insert y is equal to, and in brackets 10 minus 2x, and then multiplied by 20 minus 2x, and multiply that by x. You can see that I'm getting a graph right here. This is my graph over here, and I can't really see anything. I just see two lines, and there's a good reason for that, and the reason is because my window is a little awkward. It kind of starts from -10, it goes to 10. My y value, my volume calculated from last set of questions, I had some volumes around 144. So I kind of need to change my window a little bit. And on every calculator is different, so you need to make sure that you're looking at your calculator on how to change the windows. But here I will go to the settings, and I will change my x-axis. Yeah, I already said that the minimum x value is 0 and the maximum is 5, so I'm just going to insert that. Sometimes you can put in 5 or 6 if you want a different value, so I kind of want to go a little bit more in this case, so I'll just do 6. And my y value in real life situation, my minimum volume is actually 0. So I can put in a 0, or just so that we can see everything in the graph, I'm just going to put -5, just so that it shows here. And for the maximum, I'm just going to choose different values, and sometimes I have to try different things for it to work. You can see that 200 is nice. I can see that maximum value over there, but I will just go a little bit higher so the graph looks a little bit better. 250, fantastic. And I'm going to close this window, and we can actually see that our graph kind of moves like this and goes down here. And what does that mean? This is saying that as our cutout length is increasing, our volume also increases. And here, at a cutout length of 1, we have a volume of approximately 144, which is exactly what we got. At cutout length of 2, we have something about 196, and then it starts to decrease right after this point, which is about 2 point something, and it decreases, and obviously when we get to cutout length of 5, we are that's kind of our limitation. So we have 0 volume at that point. We actually can't make a box. at a cutout length of 5. So how do we find this point? Every calculator has its own procedure, so you need to be familiar with that. Again, there will be a link for TI-84 and TI-Nspire. If you have a different calculator, you do need to check the instruction for that. But to find this point over here using this tool, all you have to do is actually click on it, and it will actually give you the point. And you can see that the point is 2.113 and 192.45. So this is the cutout length over here, 2.113, 2.113, and the maximum volume that you can get out of this sheet of paper or cardboard is 192.45. So if you're given this in terms of like an assessment and you need to show your work, you need to actually show a sketch of your graph. So I would just do this in blue. This is my x-axis. This is my volume, so I'm going to label it as V. And V is equal to 10 minus 2x, 20 minus 2x multiplied by x. And you do need to highlight and actually mention what this point is. And you do need a small sketch of your graph. So you're going to draw your graph like this on the paper so that we can actually see it. You're also going to label the window size that you use. So here I use 250 here, and I use 6 over here. So I'm going to show that as well, so that it kind of gives the reader an idea that you knew exactly what you were doing and you're not just plotting random things. So here it is, and this tells us that the cutout length, so this is saying that x is equal to 2.113, that's the maximum, and volume is equal to 192.45. Usually we leave our answer in 3 significant figures when we round them. So for this problem, max volume of 192 centimeters cubed is achieved when cutout length is 2.11 centimeters. So we kind of started with the example. What is optimization? Optimization is an act, process, or methodology of making something as a design, system, or decision as fully perfect, functional, or effective as possible. So in our case, we had the volume, and we wanted to make it fully perfect. In our case, to make it fully perfect, we needed to maximize it, and that was it. And this is the definition by Merriam Dictionary. And another definition that I found somewhere else says that mathematical optimization is the selection of best elements with regards to some criteria from a set of available alternatives. In our case with the open box, the selection of best elements, we were looking at the best volume. With regards to some criteria, this was the cutout length. From set of available alternatives, and our alternatives were values between 0 to 5 for our cutout length. And this definition comes from the nature of mathematical programming. Now, the steps involve sketching a model of the problem. So in our case, the model was already given, but if we were to do it, we would draw a box, and in our box we would identify, so this is step 1, is kind of to give a sketch. Step 2, it's not the most necessary one, but it's nice to know that we're trying to maximize volume. And then to identify variables for the problem, we identify this to be x, this to be 10 minus 2x, and this to be 20 minus 2x in our problem. So those are the first three steps. Step 4 was to formulate an equation, which was volume is equal to length times width times height, and that was 20 minus 2x multiplied by 10 minus 2x multiplied by x. And formulate solution and solve the problem using technology or graphing. And to solve it, what we did was we graphed it. And our graph was something like this. This was 6. This was about 250-ish, I believe. And I believe this was 2.11 and 192. And our equation here, volume, this was V, this was X, was equal to, I'm just going to write it in different order because it doesn't really make a difference which order we multiply numbers. So this was it, and the proper work is kind of shown here. And we need to write what the final answer is. So in our last question, max volume is 192 centimeters cubed, and this is I should say is approximately, so I'm just going to erase this and say is approximately 192 centimeters cubed when cutout length is 2.11 centimeters. All right, let's do a few examples. We're going to start off with this example over here, which says a city planner would like you to design a swimming area at a local beach. There is 100 meters of rope available to enclose the swimming area. The shore will be one side of the swimming area, so only 3 sides of the rectangle will be roped off. It is your job to determine the largest rectangular swimming area. So, looking at the question, let's read some of the most important parts. One of them says that you are trying to build a swimming area. There is 100 meters of rope available to enclose the area. The shore would be one side of the swimming area. And your job is to determine the largest rectangular swimming area. So let's walk through the steps. The first step is to draw out the situation. In this situation, we have a swimming. We're trying to, this is the shore, and we're trying to rope off the swimming area. And this is going to be our swimming area. It's going to have a length, and it's going to have a width. And then once we have drawn it, we are going to say what we're trying to achieve. We are trying to maximize area. The third section is to identify our variables. If we're trying to maximize our area, then we are trying to get A is equal to LW to be max. But at the moment, unfortunately, our area is written in terms of 2 variables, and we actually can't work with that. We want to change it so that we're only writing area in terms of 1 variable, so then we can graph it, and once we have graphed it, we can actually find the maximum area. 2 variables, no good for us at the moment. So what we will do is we're going to let let length or W equal to x, In this case, I will let's let L equal to X. Yeah, let's let L equal to X. It would be, you can let W equal X. It's actually a little bit easier, but I will take the little bit more challenging one so that you can see the math. So we're going to let L equal to X. So then if we do that, area will equal to X times W. We haven't really done much, unfortunately, because the area is still written in terms of two variables, X and W. We need to change this W somehow so it's also written in terms of X. So that's kind of our next challenge. So, okay, what do we do here? Well, the other set of information that we have is that the perimeter is equal to 100 meters. So 100 meters of rope is available. So we also know that the perimeter is equal to, so perimeter is actually equal to, in this case, the perimeter is this plus this plus this. So I have 1W plus 1L plus 1W. So I have 2Ws plus L. So the perimeter is equal to 2W plus L. We know that the perimeter is equal to 100 is equal to 2W, and we already said that L is X. We've done that right here. So we've done that right here. L is equal to X. So instead of L, I am going to write X. And now I am going to isolate for W, and by doing that, I will write W in terms of X. So to do this, I'm going to subtract both sides by X. And I will get 100 minus X is equal to 2W. And I just want to isolate for X over here, so I will divide both sides by 2. So divide by 2, divide by 2, the 2's cancel, and I'm left with W is equal to 100 minus X divided by 2. Alright, so now I wrote W in terms of X. So now this area over here is X times W. So instead of this W, now I can write 100 minus X divided by 2. So continuing on, a little bit of a long process, area is equal to X, and instead of W, I'm going to write 100 minus X divided by 2. Looking at the equation now, I have the area on the left-hand side, and on the right-hand side, I have X times 100 minus X. So on the right-hand side, I only have one variable, which is X, and on the left-hand side, I have only the area. So the area is written in terms of X. This is fantastic. Now I can actually put this within my calculator and find the maximum area. I'm going to put this in brackets. It's a little bit easier this way. And then let's graph this using a graphing package. Alright, so here I have added a graphing package. I am going to go to desmos.com, and I know that my area is equal to X times 100 minus X. So I'm going to put another set of brackets because there's a hidden brackets in the numerator there. And it's 100 minus X. And then I am going to divide that by it does that nicely actually. Divided by 2, and I get something weird like this. And So I forgot to actually mention, or I forgot to actually write the limitations of my x value. So let's talk about that for a second. So we know that our whole perimeter is 100 meters. So the whole thing is 100 meters. That means our length, which is the x value, cannot be more than 100, pretty much. It cannot be more than 100 because that's the length of the rope, and it can't be 0 because if it was 0, then nothing will work. So in this case, just write the limitation right here. Where should I write it actually? Let's write it here. So 0x 100 is the limitation of my x. So in my window here, I am going to, in my graphing package, I'm going to say that 0 is my minimum value and 100 is my maximum. And I still cannot see my whole graph, so in my y-axis I will use maybe, let's just use 0 for now. And for my maximum, I don't know exactly what it's going to be. Let's just guess that it's 100 and see what it will look like. 100 is still too small. How about 1,000? 1,000 is a little too small, but I can see that it's starting to show the whole graph. So instead of 1,000, I'm going to choose maybe 2,500. Oh, fantastic. So now I can see everything. And yeah, it's good enough. And I can actually use my graphing package to find this point over here, and it's actually 50, and 1,250 is my y value. Okay, so then once I have this, I'll just draw it out over here to kind of show what you need to show to show that you're doing the work properly. So here I'm going to have a graph. My graph is going to have 2,500 here, and I'm plotting the area on the y-axis, and I'm plotting the length on the x-axis. So I'm going to use x, and the value that I chose here was 100, and my graph looked something like this. And my maximum area was found to be, or my maximum point was 50, 1250, and this equation here was a is equal to x 100 minus x divided by 2. And once I have this, I know that this is my length value, and this is my maximum area. And the question asks for the largest rectangular swimming area, so you can say that the largest area is 12,500, and our units are in meters squared. So this is actually my final answer over here, and I've shown all my work which is necessary. But if the question had asked me what are the dimensions that give you the max, then I would know that this value over here, which is x is equal to 50, therefore length is equal to x, so that means length is also equal to 50 meters. And the width, I can calculate it in two different ways. One of them is 100 minus x divided by 2, which is 100 minus 50 divided by 2, which turns out to be 25 meters. And the other way I could calculate it is I know that area is equal to length times width. So that means if the area is 1250 and length is 50, I can divide both sides by 50 to get W is equal to 25 meters. So both ways work, but in this question particularly, asks us to find the largest area, and that's 1250 meters squared, and you don't actually have to show all this part of the work. Okay, our second example says that we get 1800 meters of fencing that's available to fence 6 identical pens as shown in the diagram. Explain or show or outline why 9x plus 8y is equal to 1800, and then show that the area of each pen is given by this equation, and then find the dimensions of each pen. So looking at this question, it says, first of all, we got to figure out why 9x plus 8y is equal to 1800. So we know that the total available fencing is 1800. We know that we have 1, 2, 3, 4, 5, 6, 7, and 8 y's. So for part A, we have 8 horizontal sides, which are y. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertical sides, which are x, and we have total of 1800 meters of fencing. And because of these, 8y plus 9x is equal to 1800. Fantastic. The second part of the question says the area of each pen is given by this. And this seems a little taunting at first, but it's actually not bad at all. So we kind of go and say that the area of each pen, actually the area is equal to, and the area of each pen is equal to its width times length. Our width is x and our length is y. So I will write this as x times y. We can see that what we're trying to prove, or what we're trying to show, is that the area is only dependent on the x value. But unfortunately, or fortunately, it doesn't really matter, our area is given in x and y. So we need to change this y so that it's written in terms of x. And how can we do that? Oh, the very first part kind of guided us and helped us. It was kind of a hint to how we can get there. So we know, and I'm going to write that in purple, we know that 8y plus 9x is equal to 1800. So I can actually start isolating for y by first subtracting 9x from both sides, giving me 8y is equal to 1800 minus 9x, and then dividing both sides by 8. And by doing that, I get divide by 8, and y is equal to 1800 minus 9x divided by 8. Okay, so now that I have this y value, I'm going to label this equation as equation 1. I'm going to label this equation as equation 2. And I will say sub equation number 1 into equation number 2. And I get area is equal to x. And instead of y, I'm going to write 1800 minus 9x divided by 8. Okay, we're getting somewhere. we're kind of seeing a division by 8, which is here. So we're kind of getting close to where we need to, and we kind of see the negative 9 over 8, negative 9 over 8x. This is squared. So we also see this. So what we can do here is we can do many different things, but one of the ways to do this is actually separate the 1800, separate this fraction to 1800 divided by 8 minus 9 over 8x. And I'm going to grab my pen again, and I'll keep writing with green. So x times 1800 divided by 8 minus 9 over 8x. So all I've done is I've separated this numerator into 18. I've just separated this fraction to its two parts. So 1800 divided by 8 minus 9 over 8x. And 1800 divided by 8 is actually 225. So that's fantastic. So area is equal to x. 1800 divided by 8 is 225. And this part is 9 over 8x. And it's starting to look a lot more like this. And our last step is actually to distribute the x to both part of the fraction, and I get 225x minus 9 over 8x squared, which is what we have above. So we've shown that area can be expressed as 225x minus 9 over 8x. Our final step is to figure out what are the dimensions that would maximize this area. And we do this by graphing techniques. I'm not actually going to show how I put it onto the graphing package. You should learn that. You should learn how to use your calculator to do that. So I will show the sketch of my answer once I plug in that equation into my graphing calculator. Alright, so my graph looks like this, where this part is the area, this part is x, and I used window size of 20,000 for my area and 200 for my x, and my graph looked something like this. My maximum area or my maximum point happened to be at 111 to 50. So you can see that one of my dimensions is 100. So determine the dimensions of each pen. So the x value is equal to 100, and my y value, I can either just divide this by this, and that would give me the y value, or I can use this equation over here. Really, it's completely up to you how you're going to do this. I will just use, I'll just do both actually, so you can actually see it. So it's 1800 minus 9 times x. My x value is 100 divided by 8, which is 900 divided by 8, which is equal to 112.5, or you can also approximate it to 113 if you wanted to. And this is in meters, and this is in meters. The other way you could have done this is, you know that the area is equal to xy, so we know that our maximum area is 11250. We know that our x value is 100, and we know that our y value is just y. divide both sides by 100, and you will get y is equal to 112.5, or it's approximately equal to 113. So any of the methods work. I'm going to put a big or over here because I definitely don't want you to show both. I just want you to show one of the methods. So finally, dimensions are, I'm just going to write the exact values here, 100 meters and 112.5 meters. Alright, the final question on this video says that you want to construct a new chicken coop at the side of a barn. Since the barn will make one of the sides, you only need to fence off 3 sides of the coop. The chicken coop must have an area of 128 meters squared. Let's start drawing this out actually because there's a lot of information. Let's use a different color. Let's use purple. So we need to fence off 3 different areas. This is going to be the length, this is going to be the width, and we know that our area is equal to 128 meters squared, or we know that we can write our area as length times width is equal to 128 meters squared. A clever fox, oh, this clever fox, has been trying to get into the old coop and has caused a lot of damage. Since it is likely that you will be constantly repairing this coop, you want to minimize the perimeter so that you can save money. Determine the required dimensions. Interesting. So the perimeter is equal to length plus 2w. And as we said before, we always want to write the perimeter or whatever we're trying to maximize or minimize just in terms of one variable. Right now it's in terms of 2 variables. But luckily, we can actually change one of these two into the other one simply by replacing or simply by rearranging this formula. So let's do this step by step. I'm going to use a green color and I am going to let, it doesn't really matter which one, I'm going to let the length equal x. And if length is equal to x, our first equation over here becomes x times w is equal to 128. And if I want to isolate for w, w will equal to 128 over x. I know that I'm going to write in blue now. I know that my perimeter is equal to L plus 2W. So perimeter is equal to L, which I let equal x, plus 2W, which is 2 times 128 over x. And just to simplify this, 2 times 128 over x is 256 over x. Okay, now that I have this, I am trying to find the minimum area. So let's actually bring up our graphing package so that I can show you how this works. So here's our browser. I'm just going to make it slightly smaller and I'm going to shift it to the side. I then will go to Desmos, and once I have Desmos, I'm going to enter my equation as x plus 256 divided by x. And I actually can't see anything at the moment, so I gotta change my window size a little bit. Okay, so I actually have no idea what any of the values will turn out to be, and I'm trying to find perimeter, not area. So, but I do know that the minimum perimeter is going to equal to 0, and I know that the minimum x value is going to be 0 as well. So I know those limitations. For my x value, I'm going to increase it to maybe 50, and I'm going to try different values and see when I can see part of my graph. So I'm going to change this to 200. And okay, this is not bad actually. So if I get rid of my calculator, I can actually see that my perimeter is decreasing at first as I'm changing this length value. So as I'm increasing this, the area is actually decreasing. It reaches a minimum and then it starts to increase again. So to find this value, I will use my graphing techniques, and in this case I will get 16 for my x value and 32 for my y value. Let's sketch this. So using GDC or Graphing Display Calculator using technology, I will get a graph which looks like this. And on my y-axis, I've chosen 200, and I'm plotting the perimeter, and I'm plotting x value over here, and I've chosen a value of 50. And my graph looks like a Nike sign like this, and my minimum is somewhere over here, and it has a value of 16 and 32. And the equation that I plotted was perimeter is equal to x plus 256 over x. So here it is suggesting that my minimum perimeter is 32 and is achieved when I have a length of 16. So the question says to determine the required dimensions. So in my final answer, I can say that the minimum perimeter is 32 meters. Don't actually have to write this part down because it doesn't ask you that part, but the dimensions, I know that for the dimension, actually I'll just write a concluding sentence later. For the dimensions, I know that my length, I have set that my length is actually x, which has a value of 16 for its minimum, and my width is equal to 128 divided by x, which is equal to 128 divided by 16, which is equal to 8 meters, and length is 16 meters. So therefore dimensions are 16 and 8 meters. And again, I had said that my L is x and my width is 128 divided by x. And that's how I got length as 16, because that's the x value and it's the minimum perimeter is achieved at x value of 16, and my width is equal to 128 divided by x, which is 128 divided by 16 for the minimum perimeter, when that's equal to 8 meters.